So here in part 2 of section 7a, Fundamentals of Probability, we'll finish up section 7a. The next task is to learn how to form a probability distribution. So probability distribution represents the probabilities of all possible events of interest. So in other words, we'll name some events. We might think of this as in a game, winning or losing events, which make up the entire realm of possibility. And then we make a table of a probability distribution which will contain each event and the probability for each of those events. So we have some steps here. If we can list out all the possible outcomes, in other words, write down the sample space, we will. If there are fewer than 20 outcomes, this is totally reasonable. If not, we might not want to do that step because it could be really labor intensive. So identify the outcomes that represent the same event. In other words, count up the outcomes in an event and divide by the total number of outcomes to find the probability. And we'll see this in detail in the example below. And then we'll make a table that lists each event and in another column next to it, their probabilities. Now the key thing about all this, and I'll leave it highlighted, is the sum of all probabilities in this table will add up to 1. That's just a nice check. If it doesn't add up to 1, then you know something has gone wrong. If it does, then there's a decent chance that things are going pretty well. So the example below asks us to make a probability distribution for the number of heads that occur when 3 coins are tossed simultaneously. Okay, so tossing a coin 3 times. Just to review real quick, 3 tosses of a coin with 2 possibilities in each toss. Use the fundamental counting rule that tells us there should be 8 outcomes. So now we know we can use step 1. We can list all our possible outcomes. There are only 8, so we know how many to put down. So let's go ahead and do that. So our sample space, this is not a probability distribution. This is just our sample space. That's heads, 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 tails, heads, tails, heads, tails, heads, heads, tails, tails, heads. The order doesn't really matter. Tails, heads, tails, heads, tails, tails, and tails, tails, tails. It's nice to have used the fundamental counting rule because we know when we can stop building this table. Otherwise, there might be some question as to how far we need to go and whether or not we've got them all. As long as all of these are different and there are 8 of them, then we've got them all and we have a complete sample space. I'm going to label that sample space because it is not the probability distribution. Okay, so now the events that they're asking about. So imagine it as a game. They're saying for the number of heads. So, when we toss a coin 3 times, either 0 heads can land, 1 heads out of the 3, 2 heads out of the 3, or 3 heads out of the 3. Those are all the possible events concerning numbers of heads. So let's go ahead and write that down to start to form our table. This is a probability distribution, abbreviated, and we'll have the event, which is the count of heads in this case, and then to the side of that we'll have the probability. This is what every probability distribution will look like. It'll be a list of events with their probabilities to the side. So as we said, we toss a coin 3 times. It's possible to have 0 heads. It's possible to land 1 heads. It's possible to land 2 heads. And it's possible to land 3 heads. Now, these events should be complementary in the sense that they should make up the entire realm of possibility in the experiment. And that's the case. You either get 0 heads up through 3 heads and a toss of 3 coins. Okay, so those are all the things that could happen regarding the number of heads that show up. So now to fill in the probability. Well, 0 heads. If we look at our sample space, we'll see that there's only 1 outcome that represents 0 heads. So there's 1 divided by the 8 total outcomes, so we have a probability of 1/8. For 1 heads, we need to find all the outcomes that match that event. There's 1 heads, 1 heads, and 1 heads. Everything else has 2 heads, or 3 heads, or no heads. So that's 3 out of 8. And we'll write that down. 3 out of 8. 2 heads. 2 heads is this event, or this outcome, and this outcome are in that event. So that's 3 again, divided by the total 8 for probability. 3 out of 8. And 3 heads. That's just this singular outcome right here. So 1 out of 8, and we have 1 out of 8 for this probability. Okay, this is our probability distribution, and we're essentially done with it, but I did mention that we should be able to check that all the probabilities add up to 1. So if we do that, and we add up 1/8, 3/8, 3/8, and 1/8, we should see that we get 1, 3/8 plus 1/8, and that's because this is representing 100% of the possibilities, and in fact we do. We have 8 divided by 8, using that common denominator of 8 to add all the numerators, putting that over 8, we have 1. So far it's checked out. So we don't find any errors with our probability distribution yet. Okay, hopefully we'll have some more time to do another probability distribution in a future video. There will be opportunities in the class, of course, and the work to do it. This will be a big part of Project 1, so don't forget about that when you're putting Project 1 together. What's next? Relative frequency probabilities. These are a little bit easier than the theoretical probabilities we've done. This is the second of 3 types of probabilities we'll cover in the course. Theoretical, we've just looked at a bunch of examples for. Relative frequency is second, and then we'll see subjective on the next page from this. So for relative frequency, this is a matter of observation. We're looking at an event A that's occurring in our observations or in the real world or in data that we're looking at. We look at the number of times that the event A occurred, divide it by the number of observations we made, or the number of outcomes we've got in our list of data, and the total number of outcomes in the list of data, and that's the probability of this event A. So it's easier just to see the example, I think, to understand what's happening here. So this example says for the first 45 days of summer, 20 days have had a high temperature above 110 degrees Fahrenheit. What's the probability that the following day, the 46th day of summer, will have a high temperature above 110 degrees Fahrenheit? Well, this is as simple as it looks. We have 2 values, the total number of days we've observed temperatures and the 20 days that we've seen temperatures above 110 degrees. I know that weather is a bit more complicated than this, but for our intents and purposes in this class, when we're given a problem that looks like this, we can just assume we use the information we have to do our best estimate, and that's what this relative frequency probability is. Day 46 has a high above 110 degrees, right? And this is equal to well, 20 days had a high above 45 or above 110 degrees, number of times the event has occurred. So 20 times is the case there, divided by the total number of observations, that's the total number of days. So 20 divided by 45. This number has a common factor, or these two numbers have a common factor of 5, so this cancels to a 4, this to a 9. So we have 4 out of 9. Yeah, 4 out of 9 is just fine. As a decimal, it's 0.4 repeating, but this is fine to leave it as a fraction. So relative frequency probability is that straightforward. The number of times the event has occurred divided by the total number of times observations were made. So that's the basics of that. Now, subjective probability is our third type of probability, and this really isn't a mathematical idea at all. This is just the sense that, or the sense in which people use statistics or percentages or probabilities to make colloquial statements. I'm 80% certain that I can pass my first midterm exam. Well, that's a fairly unquantified statement. I'm sure it's got a quantity in it of 80%, but nobody's actually calculated that when they make a statement like this. More commonly, we'll hear 99% of the time or 99.9% of the time. People like to say exaggerated things like this, and I think it's pretty obvious that nobody's actually done any mathematical calculation. So this is just a term that's been thrown in here, subjective probability, and it's literally just making numbers up to express how you feel about something or to further your opinion. So we won't dwell on this too long. We've just seen the definition, and let's get back to theoretical probabilities. So odds. So probability and odds are closely related. They're not the same, and that's a key thing to keep in mind. We can see that they're not the same. The odds in favor of E is not exactly equal to the probability of E, but it is equal to this ratio of the probability of E to the probability of not E. Okay, so odds and probability are not equal, but this formula will connect them. Okay, so let's look at the first example. First part of the example, we roll a 6-sided die, find the odds in favor of rolling a number greater than 2. Okay, so to write this down, these are the odds. Well, maybe we won't write the whole thing down. The odds in favor of rolling a number greater than 2, well, the formula tells us to take the probability of the event rolling a number greater than 2, divide by the probability of its complement, and I'll just write not greater than 2. We could also write probability of being less than or equal to 2 for this roll. And just as an aid, let's go off to the side. We're rolling a 6-sided die. What's the sample space? 1 through 6. We'll just assume a standard 6-sided die numbered 1 through 6. Okay, so the probability that we roll a number greater than 2, that's these 4 numbers. So that's 4 out of the 6 possibilities divided by not greater than 2. 1 and 2 are not greater than 2. So this satisfies the event, so it's 2 out of 6. Now to handle this compound fraction, we have 4 over 6 times, we flip the denominator and multiply these. Cancel 6's. We have 4 over 2, 2 over 1. We might even write just 2, but we should always remember that if we get a whole number here, we could write it as that whole number over 1, since of course it is equal to 2. Right? But we want this fraction or this ratio here because we're going to express these odds, 2 to 1 odds. Now what does that mean in the context of the problem? It means for every 2 ways there are to roll a number greater than 2, there is 1 way to not roll a number greater than 2. So for every 2 ways there are to roll a number greater than 2, there's 1 way to not roll a number greater than 2. Okay, or in this case, 4 ways to roll a number greater than 2 to 2 ways to not. Okay, but you can reduce that to 2 to 1. So that's an interpretation of odds. It's certainly not equal to the probability, right? 2 over 1 is really a value of 2. That's got nothing to do with the probability of getting a number greater than 2, which was 4 over 6. Okay, so don't confuse these two things. They are related, but they're not the same. Okay, one other example here. I'll leave B and D for the reader to attempt. I'll give you the answers here. It should be 1 to 1 and 1 to 1. A nice shortcut for the odds against rolling a number greater than 2 to do part C. Since it's related to part A, only we're changing it to against instead of in favor. Well, if you have the odds in favor, the shortcut for odds against is to flip your fraction, 1 to 2. Now if you carry out the formula given right here, you'll arrive at exactly this answer. Okay, but if you already know the odds in favor, this shortcut's really nice and you might as well just use that. So you can try both ways, or at least try the formula way to compare it to what we've got here, and you should see that you get 1 to 2 in the end. And that means that for every 1 way there isn't to roll a number greater than 2, there are 2 ways that there are. Okay, so that should conclude 7A. Keep a lookout for 7B, which should post shortly, and good luck.